So, today I'm gonna talk about the computer architecture. The uh, this is the this is computer architecture. Okay, and remember in the second lecture, I think we say that we do some runtime analysis of some algorithm, and there's something called a basic computer step, and like the these things three things are one basic computer steps, and we can calculate the total computer steps of an algorithm. So what is a basic computer steps? To answer this, we should like go into the computer architecture, and I don't know if you have heard that computers is digital and all the things are zeros and ones and all the things are discrete. Have you have an understanding of why is this?
Yeah.
Okay, cool. Okay, so you really know a lot of things, and yeah, so let's go on. So first is the to change a number from decimal to binary or from binary to decimal. And do you know about this? Like,
Yeah.
okay. Okay, binary is only zeros and ones. And this is decimal to binary. And this is binary to decimal. Right. So if you know that, I just give. And maybe this is new to you. I don't know. If you want to change a decimal number to binary, you just divide it by 2 and get 6, and the remainder is 1. Divided by 2, and 3 remainder is 0, and something like this. And you got from bottom to bottom up, okay, and you got 1101, which is binary number of 13, right? Okay, and okay, so we represent everything in computer by zeros and ones. We today only talk about storage. Okay, we store everything in computer by zeros and ones, and zero and ones are switches, and yeah, something like this, a switch, and you must have seen integrated circuit, and there are a lot of endless switches in this thing. Okay, and also in a CD. So if you make it very big, and these are 0 and these are 1, and maybe for this is 0 0 0 1 0 1 0 0 1 0 0. Yeah, something like this. I know. And every 1 0 and every 1 1 is called a bit, and a bit is just a switch. Okay, and if the switch is on this side, it represents 1, and this side it represents 0. And uh, and if you have one switches, right, you can represent n equal 1, and you can represent 2 to the 1, which is two things, right? Because it's 0 and or 1, right? If you have two switches, then you can represent four things, and it's 0 0 0 1 1 0 1 1. And similarly, if you have 7 switches, you can represent 1 1 2 8 things, right? And they also called bits, like 7 bits. 7 bits you can represent 1 to 8 things. So is this clear?
Yeah.
Okay. And remember that 1 bit is only about 1 switches, right? And 8 bit is called 1 byte. So 1 byte is 8 switches. So this is small b, this is big B. This is kind of confusing, but remember that. And there are some other confusing stuff, like something called 1 key B is 1024 bit, like 1024 switches, right? And this is for all the, you may not know what are these stuff. And anyways, anything in computers use this, like 1 key B equals 1024 bit. And some commercial people, I don't know, so now I want to sell like an integrated circuit, right? And it has, let's say, it has 10,000 switches, okay? And we want to make it like bigger, like so it can sell, like it can sell more money, right? So we divide it by, if we divide it by 1024, which is used by the computer, and we get what? I don't know. Let me check. We get this thing, right? Kibi. And but if we divide it by a smaller number, which is 1000, and we get 10 kb, right? Kb, yeah. And this is small b, remember. And this is bigger than this, so it seems to be bigger, right? So if you divide it by a small number, you get a big number. And when you sell something, like you sell some storage thing, or sell some internet speed things, so you sometimes use this, like, so it seemed to be bigger. Is this clear? I don't know. Can you understand this?
Yeah.
Okay, so when you sell something, it use 1000, so that it seemed to be bigger. And so what you buy actually, what you buy in the end is have to divide it by 1024 to get the final numbers. I don't know. Okay. And so we just do not consider this. So everything in computer is 1024, and so 1 KB, see this is a big B, right? It's equal to 8 KB, which is small b. So anyway, 1B equals 8B, and 1 KB equals 1024 B, right? And 1 A small b equal 1024 B. Yes. And there's something after this, which is KB, MB, GB, TB. Oh, this is too big. I never see this. Okay. And so now I see I have 2 to the 2 6 bit, which is 2 to the 2 6 switches. Okay. So how big is it? Like we see the 2 6 and see this is small b here, right? And 2 6, and this is x, this is y here. Okay. And so x equal 2, right? And we got this, and y equals 6, and we got this. So 2 to the 2 6 is equal to 6 4 and b. Okay, so you just 6 4 is go to here, and this go to here, right? Is this clear?
Yeah.
Okay, so let's do some exercise, like 2 to the 34. What is this?
Uh,
16 tabby, right?
yeah.
No. Gibby. 16 Gibby. Here and here, right? Okay, let's move on. So now I'm gonna tell you how to represent a text and image and audio and videos in the computers. Okay, and the first one is text. And this is pretty dumb, and people just represent. There's something called ASCII code, I think, and something called a Unicode. What are they? So ask2 is like I have 7 bits, and I can represent 182 scenes, right? And so we just represent them, and so these are 7 things, 7-bit, and the first all zeros is okay. You may not know what is not, anyways, and the some useful notation I don't know we use in computer and so this is this stuff and 0 is this stuff, okay, and some letters, and A is this, B is this. We just literally represent 180, 1 to 8 things. Like these are 1 to 8 things, right? And each have a binary number, which is 7-bit. So this is ASCII2 code. And so literally, if you have a text file including hello, and it use ASCII2 code, and if you see it in binary, it's literally this, okay, which is 5 letters, 5 characters, and 7, which equals to 35 bits. So you use 35 switches in your computers to represent hello, and there are endless switches in your computer, okay? Yeah, is this clear?
Yeah.
Okay, and other things is called Unicode, and it's obvious that 182 is not enough to represent everything in the world, and people develop something called a Unicode, and it takes 1 to 4 byte. So 1 byte is 8-bit, and 2 byte is 16, and 4 is 32-bit to represent everything in the world. So 32-bit is 2 to the 32 is 4.3. This can represent every characters in the world, including all the languages and all the emojis and other things, right? This is crazy. And okay, let's move on. And so the most the most useful one maybe UTF-8, which is 8-bit Unicode. Okay, which is this. Uh, let's have a try. So this is a text file, and it uses UTF-8 code. Okay. Let's first delete all the things inside it. And you see here it is 0 byte. 字节 is byte, okay, which is the big B. And let's find some Yesterday I find something called death. And copy all this stuff into the text file. Okay, and I Ctrl S to save it, and it's now 3KB, right? It's this big B here. So how many characters are here? Actually, I asked ChatGPT. Oh, I don't know. So yesterday when I tried this is like 2810 characters inside the text file. Okay, including the space, because you have to represent space here in the code. And so each code is 8-bit. Every character is 8-bit, right? And I have 2810 characters, so it's literally 22480 bit. So actually it takes like 22,000 switches in my computer to represent this text file. And so we divided by 8, it's 2810 byte, and divided by 1024, and we get 2.64 KB, and it's almost 3 KB. Okay, so that's why we get 3 KB in the computer. Is this clear?
Yeah.
Okay, so that's text, and then we want to represent a picture or an image in computers. So image is a lot of pixels, right? And it's 3 channel, which is RGB. And so we got a picture which have so much pixels like this, and it has 3 channels like RGB. So and we use 8-bit to represent every pixel in every signal, each pixel in each signal, right? And so for blue, there's from light blue to dark blue, like it's 0, it's 8-bit. 8-bit can represent 2 to the 8, which is 256. So in computer, everything starts at 0, and it's 0 to 255 for the value in each pixel in each channel. Okay. So there are so much pixels, 3 channels, and each channel, each pixel is 8-bit, right? So this value can be 2 to the 255 in here, right? And so we multiply all of them together, we got this byte, okay, and multiply by 8 is the bit now. And we use so much switches to represent one pictures, and this byte is divided by 1024, and then divided by 1024, we got 5.93 MB. So it takes like 6 MB to represent the pictures, which is normal in computer, right? Is this clear?
Yeah.
Okay. So we want to, so this is a little big. We want to try to compress it. Okay. Okay, there are two lossless compression algorithms in computers. So what is lossless? It's you do not lose any information of the picture. You just change the way to encode it. Okay. And there are some compression algorithm that you can lose information. For example, the picture becomes becomes like not as clear as it was. And so we only talk about lossless compression algorithm here. And the first one is, you can see that there are a lot of duplicate pixels in the image, right? And for example, in this image, there are a lot of white ones. These are white, and after that, white, and you got some red ones, right? So there are a lot of duplicate, which is white, red, blue, and a little black, right? And okay, so we represent an image to a vector here. So for example, in this image, RGB and 3594, which is three byte, right? And this is the first pixel, and the next pixel is 1976, right? And blah blah blah, and go here. We got 623, right? The next one is 13620, right? So this is how we represent a picture into a lot of numbers. Okay, and similar here. And 255, 255, 255 is white, right? And 255, 255, which is red plus green, which is yellow. I don't know. Yeah, it's yellow. Okay, so and 30 is black, right? So these are a lot of pixels in the pictures. They are represent into a lot of numbers. So you see there are a lot of duplicate yellow, like there are 7 yellow pixels, right? 1, 2, 3, 4, 5, 6, 7. And maybe we can change the way to encode it, and we can save some space, right? So we just put the count of the following pixels at first, okay? And so this is mean there's 1 white pixel here, 1 yellow pixel here, and 1 black pixel here. And we got 7 yellow pixels here, right? And 3 white pixels here, and 3 yellow pixels here. So in this way, we do not lose any information, but we can represent a picture in some shorter or some smaller ways, right? So the original, there are 16 pixels, and each pixel is 3 byte, and we compress it into like 3 byte. There are 6 3-byte pixels, and we have to represent the numbers of these small numbers, right? And 1, 7, the biggest is 7, and how much bit do we need to represent 7? Which is 3 bit, right? And because 2 to the 3 is 8, and 7 is less than 8, right? And we have 3 bit, and there are 6 places. So we just compress it into a smaller one. Is this clear?
Yeah.
Okay, so for this picture, we can say that there's a lot of white pixels, and suddenly there's some red pixels here, right? Okay, so we can compress it a lot smaller. And there is another compression algorithm which is very beautiful. That is called Huffman encoding. Okay, and still the example in the last slide. And so after we have after we look into it, we find that there's only, if we take two pixels together, okay, and there's only 4 possible combinations, okay, and this is white yellow. We call it W gun, WY, okay, and this is BY, this is YY, this is YY, this is YY. So we take every 2 pixels together, we find that there are 4 YY, yellow yellow, and 1 white white, 1 black white, which is here, and 2 white yellow, which is here and here, okay. And maybe we can just represent these things, okay. Right, there are only 4 things to represent, and we need a dictionary to look up them, like so I'm gonna introduce something called Huffman encoding. Let's add a new page. So we have 2 W white, 1 black white yellow, and 4 yellow yellow, 1 W W. So the naive idea is that there are a lot of yellows, right? And we want to represent them in a smaller or shorter bit, right? And here, like if we represent, like for example, if we represent yellow yellow as 111, okay, and here we need to store them as 111, right? And yellow yellow like appears the most of the times. So if we want to save the space, we might want to represent it as 0, and we got 0, 0, 0, zeros. And maybe we call some other things like appear a little times, only 1 times, and we call it 111. So this is 111, so we can save space, right? So if it appears like less times, 1 times, so it doesn't matter if we give it a long encoding, right? And if we got something appears a lot of times, so we would try to give it the as little bits as possible, like 1 bit, right? So how to do this? We use something called a Huffman encoding algorithm, and I got the last one. So we first use the least ones like B Y W W. We make it into a tree, okay. And this appears 1 time, this appears 1 time, so they totally appears 2 times. And then we got WY here, which appears 2 times. We got them together, they appear 4 times, right? And the YY appears 4 times. And we got them together, so totally they appears 8 times. And we got a tree here. Okay, this is called a tree. And so then we just encode them. Like this is 0, this is 1, this is 0, this is 1, this is 0, this is 1. So now we got YY, which appears the most of times, so its encoding is 1, okay. And WY, its encoding is 10, 10, okay. And the BY is 110, right? And WW is 111. Okay, is this clear?
Yeah.
So in this way, this appears the most of times, and it uses the shortest encoding, and this appears like less times, so it used the longest encoding. Okay. Yeah, so we got this. And in this way, we can literally represent this like 48 byte scenes into 40-bit, okay? Which is a lot improvement, right? A big improvement. And so this picture becomes 1011100001111100. Okay. But you may wonder, like, how can I know this is like 1 bit or 2 bit or 3 bit? It may got conflict, right? Because you only give me like these numbers. How can I know I should use 2 bit or 3 bit or 1 bit for the encoding? So how can I decode it into this thing? And actually, this is very neat. We can put it here. So this is a tree, right? And we can just write some code like using if, else if, and so we just go into the tree. So this is the beginning, which is 1. So we go to 1 and 1010. So it's WY here. Okay. Because if we go to something, then we say it. And we start the next one, which is 1, 1, 1, 0. So we go 1, 1, 0, which is BY, right? So actually, there's no conflict problem. And this is because it is prefix free, which means that one encoding is impossible to be the prefix of another encoding. This means that if we have 1, 0 and we do not have 1, 0, 0 encoding. So this is prefix free, like one encoding is not the prefix of another encoding. So there's no conflict problem in decoding, so we can decode it. Okay, is this clear?
Yeah.
Okay, so in this way, we can represent the picture in 14-bit, but we have to also store the dictionary to look up it, right? So 0 represent this, yellow, 1, 0 represent this. We have to store it, otherwise we do not know how to decode it, okay? And so this is a dictionary, we also have to store it, and so we have 14-bit plus, here's 9-bit, and here is 8 byte, okay, 8 multiplies 3 byte. And anyways, we compress the original pictures into smaller ones using the Huffman encoding, right? So how do you think about it for this picture? Maybe we can just represent white as, because white appears the most of the times, I think. So we represent it as 0, and I think gray is another, the second color that appears the second most, and we say it's 1, 0, right? And this is 1, 1, 0, right? And this is 1, 1, 1, 0, and this is 1, 1, 1, 1, right? Any other colors? No, any other colors. So we can represent the colors in this way, and we can compress the picture a lot and do not lose any information, right? Okay, is this clear?
Yeah.
Okay. So next we want to represent some audio. Okay, let's move fast. Okay, and an audio is something like this. So we'll just sample it. You must have seen something like sample rate. We sample 44,000 samples per second. Okay, so and every sample is represented by 16-bit. which is called bit depth. And 16-bit, what is 16-bit? It's so 16-bit can represent 2 to the 16 values, right? And so we literally samples like every second we have 44,000 samples, and every sample is represented by 16-bit. And so we have a lot of values here, which is 2 to the 16 possible values. Okay. And this is like 44,000 per second. Okay. So we can take some audio signal, which is analog into digital. This is digital, right? Can you understand this?
Yeah.
Okay, uh, and there are two things in audio, which is so the height of the signal or something here, they are the amplitude, right? And the frequency is how fast how I don't know, like this is a slow frequency, right? And it's a low voice, and this is a high frequency, and it is a high voice, right? So we can. So the reason why we have to do so many samples in 1 second is to, like, we have to like get the frequency information so we can know how fast the thing is, like the frequency of the voice, right? And so there are two channels, which is left and right. So typically a music, which is 4 minutes, and so 4 minus 60 seconds per minute, and this is 16 seconds. This is 4 minutes, and this is the sample rate. This is the bit depth, right? So every sample is represented by 16 bit, and there are two channels. So we got, which is a typical file, like for 40 MB for one music, right? Okay, is this clear?
Yeah.
Okay, then we will try to represent some video. Video is just like a lot of pictures plus the audio, right? And we see that an image is 6 MB, and the frame rate of an audio, which is 13 pictures in 1 second, right? And so 1 minute is like 16 seconds in 1 minute and 30 FPS and 6 MB, and we got very large. Okay, and remember that the picture is something like 1080p, I don't know, and plus audio. So, and actually in our daily life, the video is much smaller than this. So there's no way that 1 minute's video is 10 gigabytes. Okay. So actually we do not represent videos directly as a lot of pictures. And there's something called a bit rate. And what is a bit rate? So actually, in a video, like you can imagine that you have 30 pictures in 1 second, right? And probably, and for most probability that the pictures do not differ much from each other. Like you have 30 pictures in 1 second, so cannot differ a lot from each other. So maybe we can just compress them by just storing the changes between each pictures, right? Like I have a picture and there's car moving from left to right, and between each frame, and only the car is moving, right? Every other thing is still the same. So we can only store the moving part, maybe. And in this way, we can compress the pictures a lot. So we just introduce a new thing called a bit rate, which is the like the like the I don't know, uh like if the bit rate is 8 m bit per second, which is m byte per second, 1 m byte per second divided by 8, right? And 1 m byte per second, it means that 1 minute's video is represented by 1 MB. Okay, so this is bit rate. And so in this way, 1 minute's video and with bit rate 1 Mbps, it's 16 MB. Okay, and plus audio. So that's a lot smaller, and it's normal in our computers, right? Okay, so that's how we represent videos. Is this clear?
Yeah.
Okay, then that's the last part, uh, and we have already introduced binary and decimal, right? And there's another thing called hex, which is base 16. And it is often used for human to look at long strings of binary numbers. Like for hex, it has 16 digit, right? And after 10, we use A, B, C, D, E, F. Okay, and AS10, BS11, similar to that. And if we have, so 0x is some prefix, and it is telling you that you are using hex here. So we got A5. A5, what is A5? A is 10, right? So 10 plus 16 to the 1, and 5 plus 16. Multiply 16 to the 0, which is 165 in decimal, right? Can you understand this?
Yeah.
Okay, and so there is some tables to this, and you see that every 4 digit of a binary number is to 1 digit of, okay, one digit of hex numbers. Okay, so but if you like put them to decimal numbers, somehow it goes to 2 digit and it's confusing. So every 4 digit numbers goes to one hex numbers, hex digit. Okay, so if we have 0 1 0 1 1 0 1 0 0, anyway, 1 0 0 1, this is a binary number and it's impossible for human to read it, and we can just got them. Okay, let's make it. Okay, so this is 1 digit of hex. This is 1 digit of hex. This is 1 digit of hex, and we put some 0 behind it, and this is 1 digit of hex, and it goes to like 0 1 0 1. Where is it? It's 5, right? And 1 0 1 0 is A. 0 1 1 0 is 6, and this is 1, right? So this binary number is equal to 1685 in hex, okay? And this is very convenient for human to read, right? And you may also see some colors. This is some color, so every colors have something like this, right? This is actually the hex numbers, and D0 is so D is 4-bit, 0 is 4-bit, so this is 8-bit. So 8-bit is 0 to 255 for red, okay, and this is for green, this is for blue. This is how we see some notation of the color, okay. It's literally 3 channels, and each channel is represented by 8-bit. Okay. Is this clear?
Yeah.
Okay, cool. So that's the all the things.